Hello, I'm Derek Arden, and welcome to Monday Night Live, where I spotlight leading figures from the world of education. Tonight, I'm excited to host Dr. Colin Summerhayes, one of the UK's foremost scientists on global warming. Dr. Summerhayes has ventured into the Antarctic 6 times on fact-finding missions, gathering critical data on climate change. This evening, Colin will share insights from his extensive research and experiences in the polar regions and what the world is doing about our heating planet. Dr. Summerhayes' latest book is called The Icy Planet, Saving the Earth's Refrigeration. Colin, welcome to Monday Night Live.
Thank you.
What's really happening with global warming?
Right. Well, I talk about this quite a lot because what we're facing is the gradual melting of ice, and that leads, amongst other things, to rising seas. This is all a function of global warming. And it's an important subject because it relates to not so much to the climate that we will experience, us older folk, but particularly to the kind of climate that our grandchildren are going to experience. So in a sense, you could think about this as learning about risk management for your grandkids' world. That's a picture of my book, The Icy Planet. And just to mention that my credentials are I'm a researcher from the Scott Polar Research Institute of Cambridge University. But one of the key messages that I have for you is that it's not all doom and gloom. It's not the end of the world, and Not the End of the World is the title of a very recent book by a woman called Hannah Ritchie, who's a senior researcher at Oxford University. And the little subtitle down at the bottom says, How We Can Be the First Generation to Build a Sustainable Planet. So this is all a very positive message, sort of hidden away amongst what a lot of people do see as doom and gloom. So what I'm going to show you here is this slide is titled Climate Damage. And this is about what the group looking at all this, international group called the UN Framework Convention on Climate Change. Up at the top left there, it says UNFCCC. And these are the people that bring representatives of all our governments together to consider what are we going to do about mitigating all this sort of problem. And the one thing they decided back when they met in 2015 in Paris was that ideally we should try not to allow the climate to warm to an average of more than 1.5 degrees centigrade above what it was in about 1900. And we should ideally not allow the climate to go as far as 2 degrees above what it was in 1900. Now, this is quite a challenge, obviously, fiddling around with the climate system. And there are a lot of people who say, well, yeah, we humans are too puny, we can't do anything about that. But in fact, it turns out that we can. This is a picture of the global temperature change from about 1950. So all the little black dots are the average temperatures of those periods, and they're connected by the blue lines. And the red line is the average that runs through these. And the green line, you see, there is actually a ruler line that I put on there, and you can see how the green ruler line projects itself after 2010. It projects itself into the future. You see that projection up here. So if things were continuing the way they were between 1970 and 2015, we could expect to get to about 1.5 degrees by maybe 2050. But it turns out in recent years, you see all these dots and purple things between about 2015 and now. And that tends to suggest that we're actually, the rate of climate warming is accelerating along the yellow curve that you see here. So this is a general concern, and we want to know what we can do about that. So moving on, then, how is this affecting different places? And what I've done here, you'll have to, those of you in America or South Africa will have to excuse me for showing you the Central England Temperature Database from 1659 right up to 2022, but it is the longest temperature record of anywhere on the planet. And what you see here is the departures on the left-hand side, the departures from the norm, which is the black line across the middle. And the norm was the average from 1961 to 1990. So that gives us, looking at this graph, which goes from 1660 at the bottom left to 2020 on the bottom right, you can see that for most of this period, the color was blue below the line, and that tells us that the temperatures were cooler by up to about 1 degree for most of that period, right, almost up to 1900. And then after 1900, things started to get a little bit warmer. By 1940, you can see a little blip there above the line, and then things sort of dropped back a bit. But by 1970, they were ramping up again. And so what we saw was that since 1980, we've had temperatures that were 1 degree or more higher than they were in 1900. So this is the global curve for global warming translated into local data. And we've started to see real big records. In the UK, we had a heat wave record in July 22. In the UK, we had the hottest June ever in 2023. The world's hottest day was July the 4th, 2023, something to celebrate in the United States, no doubt. And 2023 turns out to have been the warmest year globally. So moving on then, oops, we jumped, well, no, we're going back. Sorry, the wrong way. Here we go. There we are. So because I'm in the UK, I'm going to show some UK data. So on the left-hand side, you see the flooding that we had in England and Wales in 2023. And that's partly because when you have very warm temperatures, a lot of the ocean evaporates and the water gets into the air and the winds blow the water vapor around and it gets into clouds. And then, they dump their water on the adjacent land. So we have pretty wet February. And then on the right-hand side, you see we're going from around about 1965 right up to this year. And these are the winter. This is the number of ground frost days per winter. So you can see how it's declined from about 60 in the mid 1960s all the way down, follow the dashed line, fluctuating during the year, but it's now down at about just over 40. So we've lost the number of frost days. And March 24 was the warmest yet globally. So moving on, then we've got this picture. This is what the oceans are doing. Now, you don't often see this kind of data, but on the left, what you see is all those gray lines, and along the bottom scale, you're going January, February, March, April, May, right the way through to December. And up the left-hand side, you're seeing the ocean temperatures for those periods. And all the gray squiggly lines are the years between 1979 and 2022. And you can see they occupy a sort of band roughly centered just below 20.5 degrees centigrade. And what you see in red is what happened in 2023. And you can see there was a really big departure from what had gone before in 2023. And there on the left at the top is 2024. So the temperatures in 2024 in the ocean on average are very much warmer than what they were for this whole 1979 to 2022 period. And when you look at the figure on the right, which is the global map, you can see where the temperatures have been most. And so what we see from the brownish colors is that the Pacific Ocean, the equatorial Pacific has warmed up. The area of Japan, which is up at the top left, has warmed up. You can see quite a lot of warming on the right, leading across the Pacific to China, past Japan. And then in the Indian Ocean, you've got some brownish colors and also quite a lot going on in the Atlantic Ocean. So we see fairly large areas of the ocean which are significantly hotter than usual. So we know that things are changing both in the air and in the ocean. And so what many scientists do is they relate this to the changes that have taken place over the past 150 years. And what we're looking at here at the top left is the burning of fossil fuels. So back in 1850, all that we were burning as part of the Industrial Revolution was coal. That's the orangey color. And you can see the way that that grew slowly through time to the red line, which is the vertical line. That's 1950. And then after 1950, you can see that coal use actually began to increase really quite significantly. And there's quite a big jump on the right-hand side in the modern era. When we look at oil, we weren't using much oil and petroleum back in between 1900 and 1950 because, the population was smaller. There weren't so many cars and trucks and airplanes around. And so, we didn't burn all that much. But after 1950, we started burning tons of this stuff, and so oil became a huge additional contribution to the burning of fossil fuel. And then finally, the sort of purpley color, which you can see there was a little bit burnt back here in 1923 to 1950. That was natural gas, and that too has increased, as you can see, going up here to the point where many countries are now burning quite a lot of natural gas. So it turns out that if you take all of the fossil fuel that we've ever used, more than 90% of it has been burned since 1950. Now, looking at our audience today, I can see that several of you, like me, were probably children in 1950. So you could say all of this change really has happened on our watch. It's been an enormous change. And many sociologists are referring to this as the Great Acceleration. That's something for you to Google. On the right-hand scale, what you see in the right-hand corner is methane. That's methane is natural gas, and we can see how going from 1850 right up to today on the right-hand side, the blue curve shows you quite an acceleration in methane. That's natural gas getting into the air. And a lot of that comes from tropical wetlands, but equally, a lot of the more recent stuff comes from leakages from the fracking industry. Fracking is a process where you bring gas out of the earth and you put it in pipelines and so on. And these tend to be not particularly well maintained, so we got a lot of leakage. Now, when you burn fossil fuels, what you get as a byproduct is carbon dioxide. When you burn methane, you also get carbon dioxide as a byproduct. So these things, these two gases, methane and carbon dioxide, are what we call greenhouse gases. They absorb the heat coming off from the surface of the earth and they re-radiate it in all directions. And that's what helps to keep our climate warm. Now, you see in the bottom right, there's this little box here. And what you see is the countries listed along the bottom, starting with the US on the left, then China, India, Russia, and so on. I'm sure you can read that. And these are the cumulative amounts of fossil fuel carbon emissions in tons of carbon per person from these different areas. Now, it's not really surprising since the UK and Germany and France and the United States were really the forerunners of burning fossil fuel because we were the countries in which the Industrial Revolution happened. And so we still have a major contribution in the atmosphere from what we started doing back in the 1850s. Where is China? That's way down here, that little red blob on the left. And where is India? That's that little yellow blob also down on the left. But these are big countries that want to industrialize, and those amounts are obviously going to grow with time. So we're still using fossil fuels extensively, and we will probably continue to do so for some considerable time. So what geologists are interested in is what were we doing in the past? And the way we get to that is we drill these massively long cores in Antarctica. So you imagine a drill rig sitting on the Antarctic ice and it's drilling down with a hollow drill bit. That's a drill bit with a hole in the middle. And what we can do with that drill bit is we can recover a solid core of ice in sections about 1 meter long. We take those to the lab. And here what you see on the right-hand side is the hand of somebody from the British Antarctic Survey, based in Cambridge, and he's holding the slice off the end of one of these cores. And if you look closely, you can see it's full of little, I don't know, they look kind of like nodules, don't they? But actually, these are bubbles of trapped air. So this is fossil air. Now, who imagined that we could ever find fossil air? Certainly I didn't. But since about 2006, that's what we have been finding. So in the lab, we can analyze this air, this fossil air from previous times, and we can see how much of it there was in the atmosphere. So on the left is this graph. It goes from the year 2000 on the right to the year 1000 on the left. And up the left-hand scale is the amount of parts per million of carbon dioxide in the atmosphere, going up to 400 parts per million. And what you see where it says 280 on the left-hand scale, you follow that off to the right and you see all these colored squares and greens and purples and black dots. Those are the amounts of carbon dioxide in a number of very different ice cores from different parts of Antarctica. And they all show the same thing, that there was in the air right up until 1769, there was about 280 parts per million of carbon dioxide in the atmosphere. And then 1769, it starts to increase, and it increases more or less exponentially. And then the red data from the ice cores map on to the blue line, which is what we've been measuring in the air since 1957. And for the gentleman from Hawaii, a lot of this data comes from Mauna Loa, one of the big Hawaiian volcanoes. Now, so where are we now? Well, we're nowhere near 280 parts per million. We are up at 425 parts per million. So what this tells us is that by burning fossil fuels, we are putting carbon dioxide into the air at a rate of 20 parts per million in about a decade. And the fastest that nature did it was 20 parts per million in 1,000 years. So we're doing this 100 times as fast as nature. So you might ask yourself, what happened in 1769? Well, that was basically when James Watt patented his steam engine and everybody wanted one. And of course, they burned wood, but they also burned coal. And so there we start to get our carbon dioxide. So what's the result? Well, what this shows you is the ice, and at the top is on the left is green is Antarctica, and the colors that you see there are the topography. So red is quite high topography, that's above 2,500 meters, and the bluey turquoisey color is down around 1,500 meters, and then the dark blue is much lower topography. So you see there's in Antarctica, there's a huge mass of an uplift on the right-hand side, and the ice there is about 4,900 meters thick. So it's so heavy that it depresses the land underneath by about 2 kilometers below sea level. So if we were to melt all of that ice on the right side there, our sea level would go up by about 55 meters. That's not likely to happen because this is certainly a very cold place. What is more likely is that the bit on the left, we call the bit on the left West Antarctica. We call the bit on the right East Antarctica. So West Antarctica, as you see, very much lower topography. If we were to melt all their ice off that side, sea level would go up by about 5 meters. What about Greenland? That's in the lower figure. Again, you see the topography. Greenland is quite high down its central core. And much lower around the coast, and it's already losing ice. If it were to lose all of its ice, then sea level would go up by about 7 meters. And indeed, what geologists recognize is that in the past, in particularly warm periods, Greenland has melted away entirely, and West Antarctica has melted away entirely. And you can see by adding 7 and 5, you get to 12 meters. And when we look at the way sea level has changed in the fairly recent past, we can see that during warm eras, it went up by 10 to 15 meters. So this is likely to be in our future at some period, but the rise will be slow. This is the kind of rise that will take place over 300, 500 years. So we won't be around to see that, but our descendants will. So where's it all coming from? You look at the graph on the right. This goes, as you see at the bottom, from 1992 right up to 2021, and Greenland is the blue line. So let's follow from the 0 point in 1992. We see what's the blue line doing? Well, not much change right up to 2003, and then you get this really steep drop off going down to the right, and eventually ending up down here. So if you read off on the left-hand scale, that is a loss of 5,000. So what's 5,000 mean? Well, it's 5,000 gigatons, and a gigaton is 1 billion tons. I've no idea how many African elephants that would be, but probably more than all the elephants in Africa. And then on the purple line, this is what happens in Antarctica. So the same period from 1992, we see the purple line is sort of flat till we get to about 2003, 2004, and then it too starts to dive off, but just doesn't dive quite so steeply and ends up over here on the right-hand side. And if you read off back to the left, that's about 2,500 to 3,000 of these gigatons. So altogether, the melting of Greenland and Antarctica has added something like 7.5 of these billions of tons of ice melted into the ocean, which helps the sea level to go up. So what has sea level been doing? Well, here we're looking at data from this this is data collected by the University of Colorado at Boulder, and it shows the satellite data from the sea surface. So it was hard for me to imagine when I first saw this data that a satellite up at about 100 kilometers above the Earth could actually measure the height of the sea level in millimeters, but indeed it can. So what we're seeing here is the rise in sea level measured by the satellite since 1993. And you see these black lines shows you the sort of wiggly line, which is more or less straight because that purple line is my ruler. And it shows that there wasn't all that much change as we went from 1993 right up to about 2008. And you can see here it says the rate of rise 2.1 millimeters per year up to 2002, 2.9 millimeters per year up to about 2012. And then you see this really big departure of the black line, which is the measured rise, from the ruler line. And so now the rate of rise is 4.4 millimeters per year. So much the same as we saw with the temperature curve, there is an acceleration in the rate of rise of temperature. There's equally an acceleration in the rate of rise of sea level. So there's a big question for engineers responsible for coastal defenses. And one of those is, what about all of our coastal megacities? How will they cope with rising seas? And of course, being here in the UK, we're very interested in London. And if London got flooded by a rise in sea level of about 2 meters or something like that, this would be very expensive. It could cost us 30 billion pounds or 2% of GDP. So to stop that sort of thing, back a couple of tens of years ago, engineers built the Thames Barrier. That's this funny structure that you see here. And the barrier will rise when there's a forecast of a storm surge coming down the North Sea. But what we now know is that sea level by 2100 is likely to rise by about the same amount as the barrier was built to withstand. So it was built to withstand a storm surge rise of 2 meters. What we now have to add to that is the rise in sea level of another 2 meters, so 4 meters in all. So we'll have to completely rebuild this barrier to protect London. And on the right-hand side, you can see the blue areas are what would be flooded if sea level went up by about 7 meters. So it doesn't matter where you live, Antarctica is going to affect you. I could have shown you pictures of the Florida coastline, for example, which would look very similar. So we know that there's a potential problem. So this slide is entitled The Three Wise Men. I'm assuming you can see that. And basically, they are right about how to live sustainably on planet Earth. I'm sure you're all familiar with the guy on the left. That's David Attenborough. Up until about 10 years ago, he didn't believe in global warming. He thought it was a hoax. But then he became convinced by the data and how it was affecting wildlife. So now he's a convert to the fact that we have global warming and it is going to affect life on the planet. That's a very interesting book, very easy to read. In the middle, this guy, Mark Carney, is a Canadian who until recently was the director of the Bank of England. So he's a hotshot economist. And what interested him is, what does all this mean about our values? And so, economics helps us to see how our values are being applied in the marketplace. And so his book is a very interesting take on, what we do with money, what financialization of the economies around the world has done, and how we can escape from the fact. I guess some of you know that in economics, you don't value the environment. It just doesn't have a value. And so part of his message is we ought to value the environment. And if we did value it, then we wouldn't be buggering it up as much as we are. Bill Gates, everybody knows who Bill Gates is, and his book's very good. He's a technophile. He loves technology, and he's convinced we have all the technologies we need to start avoiding a climate disaster tomorrow, or well, today. So, we have solutions, we could be applying them. So all these books give you different perspectives on this whole business. So going back to our graph from earlier, there's the temperature rise since 1950. There's the projection, the yellow line. And you can see that already, if you look across to the left-hand scale, 1.5 is the amount of rise that we're currently close to. So we're already at the lower limit of the UN Framework Convention on Climate Change, which worries governments around the world. And they're also worried about 2. And you can see where that yellow line is leading. If you follow up the yellow line, we're going to get to a rise of 2 degrees centigrade by about 2040. And so this is a worry. So what governments have done, they sit around the table once a year negotiating, and they decided that what we can do is we should, if we can keep putting carbon dioxide into the atmosphere, burning fossil fuels, but we have at the same time to take out the same amount as we put in. And that's what net zero means. Net zero change in the absolute amount of carbon dioxide in the atmosphere. However, if they were to talk to the scientists properly, what they would realize is that by maintaining the current fairly high level of carbon dioxide in the atmosphere, it would continue to melt ice and keep the planet warm. So to get down to 1.5 degrees or below, we will need to pull carbon dioxide out of the atmosphere much more. And that means that's what this term negative emissions means. So moving on, let me show you what we're doing in the UK. On the left-hand side, you see a graph, and it shows from 1996 up to 2019, and it's the amount of materials that we burn to create our electricity. So yellow is renewables, that's wind and solar. So you start over at 1996, very, very little of our electricity came from renewables. By about 2006, however, under the influence of Boris Johnson, we began to increase that. And you can see that by the time we get to 2019, we're already up to producing 50% of our UK electricity from renewables. Obviously, we are still burning some gas, and some of this comes from nuclear and so on. Where is it coming from? The little map in the middle shows you in red, the red dots are where there are onshore wind farms, and the blue little squares show you where there are offshore wind farms. But the government in the UK is now intending to go to these very large red areas, which you see in the right-hand map of the UK. These are all large offshore areas on which we will be licensing territory for the building of massive wind farms, which will help to put up this, the orange color on the left-hand graph will help to get it up to about 80% of our electricity coming from renewables. We've already started building wind farms on the Dogger Bank, for example. Okay, so what can you or me or any individual do about all this? Obviously, what we've been talking about is what governments can do, because governments have the ability to do very big things like landing men on the moon and all that kind of stuff. But, you know, we can all do something at our own level. We can insulate our houses better. We could add solar panels. Solar panels have now come down in price absolutely amazingly. They're now really rather cheap. And the payback time, if you put solar panels on your roof, it used to be about 10 or 15 years before you recouped your cost. Now it's more like about 8 years, so it's real improvement. You can also fit something called a heat pump, which will help to keep your house warm in the winter and cool in the summer. You can change your automobile. You can, instead of driving a petrol or diesel vehicle, you can drive a hybrid or a fully electric vehicle. Trees eat carbon, so you can encourage trees to pull carbon dioxide out of the atmosphere by planting more of them. And in the UK, one of the things that we're busily doing is planting hedgerows. It's funny, you know, governments at one point, this is 30 years ago, I think, the government in the UK encouraged farmers to actually pull the hedges out so that they could plant right up to the edge of the field to get more growth, you know, make more money out of plants. However, now the government is saying, oh, no, we reverse that. You know, we've got to plant hedges because hedges are better for biodiversity, better for wildlife, and also the little trees. And so they eat carbon dioxide. So you can also make demands of government. You can tell government what you want. You can, if you don't want to do it yourself, you can join a group. In the US, I suppose you'd have the Sierra Club. In the European area, you have Friends of the Earth or the Worldwide Fund for Nature, WWF. Groups like that will act on your behalf, interceding with government, lobbying basically. But also, if you're convinced about all this, you can talk to your friends, your family, your colleagues about it, and obviously you can educate children because it's their future, not yours. And there, I'd like to leave it with my first slide again, back to Hannah Ritchie. It is not the end of the world, but we have to take action if we want to be the first generation to build a sustainable planet. It's within our grasp, folks. We just have to get off our butts and do it.
Colin, that was fantastic. Do you want to put the slide up from your latest book? Because I know your latest book is easily readable for everybody if they are interested in this
Yeah,
subject.
sure.
When we spoke about it last
Yeah.
week, you said it's not an academic book, one of those ones that I wouldn't want to read. It's an easily readable book. Well, congratulations on that.
Very good.
I saw it was on Amazon this morning, so it's
Okay.
easy. Couple of questions from me before we finish. So it's not all doom and gloom, despite what we read in the newspapers. And the sea level does seem to be going up a bit quick, though, doesn't it? You know, I mean, you that Thames barrier statistics, 2 meters, and it's already gone up another 2 meters. That's pretty serious.
Not yet, not yet. It is likely to go up by an extra 2 meters by 2100. That's the end of this century. So, given the way it's increasing at the moment and steepening with time, we expect it to be around about an extra 2 meters by the end of the century. So, things are going to have to change. Think of all the cities that are on coastlines. So when you've got New York, you've got San Francisco, Los Angeles, all these big places, Mumbai, Cape Town, they're all on coasts. They're all down at water level.
They are. They had to be, didn't they, traditionally? Because
Yeah,
that's where the coal came down the coast,
yeah, that's it.
causing this problem. How come David Attenborough didn't buy into this until 10 years ago?
I think he was influenced by people around him. There was a certain amount of denial going on. One of the principal people in the UK who runs what's it called this, the Global Warming Policy Foundation. It's Nigel Lawson, who is Lord Lawson, who is former Chancellor of the Exchequer under Maggie Thatcher.
Yeah.
And so he spreads the idea that there's nothing to worry about, chaps. No, it's all jolly good. It's probably natural. It's probably not us. And people like Attenborough, who wasn't a climate scientist but a biologist interested in wildlife, took that on board until one day he woke up and smelt the coffee.
Hmm. Can you stop sharing your screen, Colin? Because that would
Yes.
be really
Yes.
useful now. And why is West Antarctica melting quicker than East Antarctica?
It's lower, so it's warmer. And East Antarctica is very high. It gets up to a total height of about 4,900 meters. And as you go up mountains like that, every kilometer you go up, it gets colder by 10 degrees. So it's pretty cold at the top, makes it much more difficult to melt.
Mm.
But it's melting around the edge. And most of the low stuff around the edge is in West Antarctica.
And the final question from me is India and China. I was surprised about your statistics on India and China. I mean, they're almost half the world's population, aren't they? And won't they want to catch up on us? Because clearly America, the Western world are the culprits here.
Well, let's not talk about culprits. We started the Industrial Revolution, and the Industrial Revolution has led to us all having the fine lives that we have now, with all of our health gains and longevity and all of these other things that we benefit from. So, I don't want to knock that. It's just that these other countries like India and China would like to have what we've got. And the only way they're going to get that is through development. However, in China, they've become more affluent because, well, let's just back off a bit. With Ronald Reagan and Margaret Thatcher, what happened was industry got deregulated, particularly manufacturing. Where did the manufacturing industry go? It all went to China. okay, because of cheap labor. And so a lot of what the Chinese do is actually making products for us. So you could say, well, their emissions are actually ours, you know, we just don't count them, but we should, because they're making stuff for us with what used to be our manufacturing industry. Um, so that's one point. But as the Chinese individuals have got more affluent, they've been visiting places like the US and Canada, Britain, Western Europe, and they see how clean our environments are, how clean our air is. And they want the same. They don't want, you know, the sort of crap that you would have experienced in China a few years ago. I can remember how dirty the air used to be in Beijing. It was awful. It's a hell of a lot cleaner now. And these kids, you know, they're telling Xi Jinping, come on, man, you know, we want a clean environment. What are you doing? You know, let's have more solar, let's have more wind. So China is now the major producer of wind turbines and solar panels and electric vehicles. It's moving in that direction. And gradually that will overtake the old, what you might call the old-fashioned China, which was when lots of funny little industries in backyards were burning coal to produce pig iron. They're tending not to do that. They're shutting those down. So China is changing.
Wow. Colin, we're almost out of time. Can I thank you so much for a fascinating presentation, and one that sort of opened our eyes to it on the basis of there's a lot of misunderstanding about global warming, I think, and a lot of panicking, etc. And it's very clear the way you presented it with such fantastic graphs. So can I ask members of Monday Night Live to give you a vote of thanks in the normal Monday Night Live way? I'd ask you to stop on, if you would, to answer a few more questions off of the recording. And in the meantime, if anyone wants to get in touch with Colin, he's asked if you would put your questions through me, please. Colin is obviously on LinkedIn, but he's a very busy man with all his research. So I'll stop the recording now. Just say, if you're watching this on YouTube, listening to this on the Negotiators podcast, thank you for doing that. If you like it, please press the like button and follow the work I'm doing, the educational work I'm doing on the YouTube channel. Just follow me. That will be fantastic. Colin, once again, thank you so much for a totally enlightening presentation. We really do
You're
appreciate
welcome.
it very much.
Thanks for the invitation.